How do you explain two non-contact forces? That is, the kind of forces like gravitation or between charges that affect each other at a distance without touching. If this is ever talked about at school, it's done so within the context of something known as virtual exchange particles. A model is developed which is frankly so full of holes that it's going to leave most students, if they think about it, going, huh? How does that work? When the model for virtual exchange particles is developed in schools, it's usually done in the context of two people standing in different boats lobbing a ball at each other. As the first person, who is stationary, lobs the ball, in order to conserve momentum, they must move backwards. As the second person catches the ball, again, in order to conserve momentum, they must move forwards relative to person one. We have therefore modelled a repulsive force. The model is then further developed to say that as two electrons come close to each other, so a virtual photon is passed from one electron to the other. This idea of an actual physical particle being thrown between the two electrons raises lots of questions. Here's a few. At what point is the first photon emitted from one electron to the other, given that the range of the electrical repulsive force is said to be infinite? Does this mean that photons, say, at the opposite side of a galaxy, are emitting photons towards each other? Is it just one photon that's emitted, or is it a steady stream of photons? And if it's a steady stream, does this mean that the repulsive force is kind of pulsed as little pulses of momentum arrive at the second electron? And how do we use this model to explain the fact that as electrons get closer, the repulsive force between them gets stronger? Given that there are so many charges around, surely that means that each electron, or each charged particle I should say, is emitting photons over and over again at such a rate that surely we're going to run into conservation of energy issues. What's that you want to say, Betty? Don't be too unkind. Betty, of course, has hit on a very fair point here. Most of physics is based on models, and as our knowledge increases, so our models get better. However, all models, if you push them hard enough, will break down. So let's not be too unfair to this model that we've been talking about. It's only meant to be a very basic introduction. Part of the problem here is the way that we interpret language. So if I say the phrase virtual exchange particle, most likely in your brains you'll conjure up an image of something that's small and round and spherical. It won't surprise you to learn that actually this isn't what we're talking about. A first step in trying to extend our model might be to consider that when two particles interact with each other, most likely one of them will gain energy and the other will lose it. In a real sense then, energy has been exchanged between the two particles, and since energy and mass are themselves interchangeable, we can consider, notice I said consider, that a virtual particle has moved between the two. If this sounds like another hand-waving argument, that's because it probably is. We can look to improve our model by dipping our little toe into something known as quantum field theory. This suggests that the space all around us is permeated by fields, which in turn is nothing new because you've probably heard of gravitational fields and probably electric fields too. It's just that quantum field theory suggests that there are some other fields as well about which you probably haven't heard yet. If I gently tap a bell, a clear, harmonious sound rings out. The bell is vibrating at its natural frequency. If I now try to tap the bell at a much higher frequency than this natural frequency, then we're no longer going to get a nice simple vibration in the shell. It's not going to vibrate at its natural frequency. The vibration will be all shuddery and incoherent. This unnatural vibration can be considered a disturbance. It turns out that an electron can be considered to be a nice, clean ripple in the electron field, much like the natural frequency of the bell we just talked about. A virtual particle can be considered to be a disturbance in the field rather than a nice ripple in the field. As such, it has different properties to the ripple. These disturbances are what gives rise to the virtual particles, although they're not particles. Since electrons are in fact charged particles, their mere presence within the electromagnetic field causes disturbances within it. And guess what ripples in the electromagnetic field are? Yeah, that's right, photons. We've said enough now about our new model to be able to use it to give us a clearer idea or a clearer picture into virtual exchange particles. As our two negative electrons travel through the electromagnetic field, they create disturbance which travels along with them and then interacts with the other electron. Remember, we said that these disturbances are what give rise to the virtual exchange particle. If you imagine an electron whizzing through the electromagnetic field with its disturbance, as soon as you take the electron away, the disturbance disappears. And this is why these particles are known as virtual. They can't exist on their own. You have to have the particle that creates them in their field with them. It's a very pleasing thing to me that many students that I teach are very interested in this particle and quantum physics area of the course. And why wouldn't they be? Recently, one of my students came to me having been taught that neutrons act like nuclear glue. He came to me and asked, well, how come then we can't keep on adding more and more neutrons in order to make the nuclei stronger and stronger? This is such a great question that I made this video to explain why.